Case 3. Case 3 is a bit easier and requires less ruler in your glasses than case 2. Okay, here's what I'm going to do. Just like with case 1, the key here is to put a line. The key here is to put a line through the center. I need a diameter. Okay? So once you put that in, if I connect up this diameter with the triangle that I've drawn, you'll notice I have a special shape. This is a quadrilateral, but it's not just any quadrilateral, right? All 4 vertices, I should label them.
Oh, it's a cyclic.
This is the original triangle, and there's the extra bit. A, B, P, C is a cyclic quadrilateral. All 4 vertices lie on the circumference of a circle. Okay? Now, you need to know this important property about cyclic quads, okay? And to illustrate it, just like with our other angle in a semicircle proof that they're all equal to 90, I want you to draw for me a little circle and draw in it a cyclic quad. What I'd like you to add onto it is all its diagonals. There are only 2. 1, 2. Now I'm going to do something very, very similar to what I did before, okay? But I'll use some colors to help me. You remember, the angles standing on the same arc, like this, they're equal. Can you see that? Right, so wherever you see that, you've got equal angles. And here, I've got a whole bunch of them. The easiest ones to see are the ones that are literally standing. So, for instance, I could call this angle here alpha, which would mean I have another alpha here. Can you see that? Same arc. Can you see it? Yeah. This arc down here is the one they're standing on. Okay? But I have other angles that are doing exactly the same thing. For instance, crane your head. Look at it upside down. Right? Can you see? I also have angles standing on the same arc here. Beta and beta. You see it? Yeah? They're standing on this arc. Right? They're both standing on that arc. And I can do this again, right? Let's see. I've got gamma and gamma. Those guys are standing on the same arc. And I can do it one more time. Watch, can you see it? I mean, they're the only angles left, right? It's going to be delta and delta. Okay, now what have I got? What have I got? I've now accounted for every angle in the cyclic quad, the original shape I drew, right? The original shape has 4 angles because it's a quadrilateral, but because I've divided them all up, I now have 8. So if I add them all up together, I've got 2 alphas, I've got 2 betas, I've got 2 gammas, and I've got 2 deltas, okay? And the angle sum of the quadrilateral, of course, is 360. Okay, so now if I divide through, right, I have alpha plus beta plus gamma plus delta. They're 180 degrees. But watch. Now, if you look at where I see these configurations of angles, for instance, because I've conveniently colored it for you, I've got an alpha and a gamma there. And in the opposite corner, I have a beta and a delta, right? I've got all 4 of these angles, right? So therefore, these angles, these opposite angles of the cyclic quad, they should add up to 180 degrees. They're supplementary, aren't they? And I've got the same thing happening up here, right? There's my alpha delta and there's my beta gamma, okay? So the whole point of that was to show, this is the property, you may remember it last year, opposite angles of a cyclic quadrilateral are supplementary, exactly right. Now that's really useful. Sorry, that's a bit messy. It's really tremendously useful in this case, case 3. Because look, I have a cyclic quad. Here's A over here, right? So if that's A, where's the opposite angle? It has a name. BPC, right? Yeah. So this is 180 minus A over here, right? So far so good. Now I have an angle in the semicircle in that triangle as well, right? Here's the diameter. And here's where I'm at the circumference, so that's 90 degrees. Yes? And lastly, I have the diameter. Okay, so now in this triangle, in triangle BPC, okay, if I look at sine of this angle over here, right, sine of angle BPC. It should be opposite on hypotenuse, right? Because unlike here, I'm actually on one of these angles on the other side, right? So it's opposite on hypotenuse. A over D. Yeah? What is BPC? We just went to length to show that it's 180 minus A. But hold on. That's sine, right? If you have sine of some angle and sine of 180 minus the same angle, those two are the same, right? Sine of 180 minus A is just sine A, right? So that's A over D, and when you switch places, you've got the good old sine rule. Okay? So whether the angle you're interested in is acute or right angled or obtuse, in every case, the reason why the sine rule works, why all these ratios are all equal to each other, is because they're all equal to this diameter, that diameter of the circle that passes through all 3 points. Okay?